G'day. Samba is a couple of decades old now. It's been around rather a long time since a gentleman sitting in a blue shirt in the front of the room decided to avoid his PhD. For a while, it was a file server, and it's gone on, and it's now many things, including an Active Directory domain controller. And a long time, we've become a domain member, and we've even come up with doing continuous integration, not nearly as nicely as the OpenStack folks were, but you know, we're getting there. It's an old project, you move slowly. But this gives you a bit of an idea of some of the versions that we've had and the time frame that we've been developing on, because we're going to look at some of those versions as we go through the slides. Samba is a C project. We've always avoided scripting languages because, well, why does a file server need scripting? We're not a desktop environment or a. And C is the portable thing. I mean, even C99 is a bit dodgy. So how did this happen? This is what happens when you run make test. Now, question for the room. How many scripting languages can you find on that screen?
Three is the general consensus.
We've got make, we've got Python, we've got Shell, Perl. And these are the ones that are just involved in running our test scripts. And we will go a bit later into how we actually use them. But it's sort of interesting, for a C project, we do an awful lot of scripting. But we've also been fairly timid with it. I mean, Samba's got a lot of restrictions. The places that we're trying to run, we don't necessarily have any guarantees about what's available. So the tradition has been to rely on POSIX shell, so people have gone through our scripts and said, no, that's a bashism, it's got to go. Make, but not GNU make for many years. We've had awk, but you've got to make sure that it works with the Solaris awk, because M4, everybody gets M4 because you've got autoconf. And of course a C compiler. So we started down this merry road, as you'd expect. You've got to have a build system for a project. So that means make and autoconf, but never automake and never libtool. Autoconf kind of went mad for us. We had to be portable to multiple versions of the autoconf templates because too many projects were re-autoconfing. You know, the thing that's only meant to be done on the developer master machine? Well, that was happening everywhere. And so we had to then be portable for the bit that was meant to be the portable bit. We ended up with 9,000 lines of custom M4, trying to figure out all sorts of things about the system. We also had sub-projects that we eventually managed to do. We were trying to say that TDB was a sort of separate project. But the main project would directly include the M4 from the sub-project. This all got a little hairy. We also did some of the more standard things that you'd expect from a project, which is auto-generate a few things. So we ran awk to go and get prototypes. This is about where I entered the project. We needed some testing. We weren't doing automated testing on a very large scale, and so we started with a small testing system which was called the build farm. Now, because we were running this on a range of platforms, I remember working on old RX boxes, some early Solaris. We had to write things in pure POSIX shell. As one of my first programming languages I was getting into, it was hairy and limiting. But we ran a number of rsync imported trees and submitted the results back to Samba. We then processed those with a Perl script and put them up on a web page. The actual tests that they ran, we used sed to work over some template files. And those template files, they just had all caps words that we substituted. It was very lame, but it was enough to be able to get our very first test. So this is how shell sort of really entered the picture in a serious way rather than just your very trivial glue. Shell scripts have grown a lot in Samba. These graphs we're going to repeat a bit as we go through. So they're the versions, much as you saw on the first graph. The oddity on the right is because Samba 4, which is the top line, has been developed in parallel with the other versions, and so there is a bit of overlap points where we actually had them both in the same tree. So it's going to look like that throughout the tree, but you'll always see the languages, for the most part, have kept on going up and to the right. For a while, we got into Scripting Language of the Month Club, a term that Tridge used in rather derisively of Python at one point. We had Python bindings. Python was the cool thing. Tim Potter was the object of that derision at the time. He'd added Python bindings to Samba 3, but things weren't maintained, they weren't loved, and Python wasn't the fad that it became later. And these were eventually removed as just unused and broken. We also had Deja GNU TCL test scripts that were added, but also unloved and not automatically run, and so broken and gone away. We even had Lua, which has been one of the more popular embeddable languages, that was added into Samba in 2008 and removed in 2009. It was hoped that it could be used for asynchronous programming to handle our WinBind stuff, but it didn't make it. But the next big dependency we decided we could actually rely on a reasonable enough number of systems with Perl. As the Samba 4 project started to take a bit of an aggressively different direction to the rest of Samba, we decided, look, Perl, it's not everywhere, it's not on the most ancient of systems, but look, we can probably assume Perl and it won't be too bad. So our build system started to rely on Perl. And this allowed us to move from a system that didn't have shared libraries, grouping of code, or anything that was in a modern build system. So the Perl worked with the makefiles in an odd and crazy kind of way to help us with some of these challenges. But we still had AutoConf, we still had M4, we just added to it. So Perl, as you can see the point in the where Perl also became a part of the Samba project. Around the sort of halfway through our recent development cycle. But this is the big area that we decided to take Perl in, is that once we started using it for the build system and it was available, an early effort for, we had the idea that we could build so much of our source code from IDL. That's the way you're meant to work for a network programming language where the specification is IDL. You're meant to then convert automatically between that IDL and what you actually put into your repository and what you build on. You should preferably do it at build time. So there was an early effort that Tridge was worked on, which was called A-parser, and it used awk. And these awk scripts processed over the IDL files and produced the results. But as I understand it, the results ended up being hand-edited, little special tweaks were done, which meant that it was no longer really generated code, it was just a templated code that was sort of hacked on. So that awk system never really worked out, but the ideas remain, particularly with Tridge, in thinking that there is the right way to do this. And so PIDL, which was a Perl-based IDL compiler of a similar age, but not previously used, was basically revived in about 2005 or so. That IDL compiler was used as is. The results became what we used, and we put the exceptions into our IDL, so there was we weren't throwing the results away. So throwing the generation work away by hand editing. We could actually go and fix the generator for problems we found later. And we now use PIDL extensively throughout Samba. Amate came up with this beautiful diagram to explain quite how many places our IDL compiler puts code into Samba. We generate up the C template for the server implementation, so this is the actual function called stubs, and then you go and fill in the results of what you actually need to do. We have client APIs for C, we have the client Python, we did generate JavaScript for a time, but it's also, we generate up multiple layers, so that as well as the most low-level calls, we generated up a proper function call interface you could use as well. And this means that a large amount of our code is auto-generated and is therefore very regular and is behaving the same way that throughout the code base. And this has been really important for allowing us to make major transformations to Samba over time. Samba, the traditional C project that doesn't do scripting languages, did JavaScript. I wasn't a great fan of it when Tridge gave compelling reasons as to why this was the right thing to do. In particular, the way that Tridge was able to integrate an embeddable JavaScript engine into Samba gave us a scripting language without these onerous dependencies, because we were still very much in the clutch of we can't have dependencies. This embedded EJS is a particular external project of embeddable JavaScript. They actually worked with us, and Tridge worked with them, to integrate talloc into their system. So despite there being bindings between us and an external language with an external memory management system, we were able to have use our internal memory management system for that. It was really quite powerful. And we had C bindings for RPC functions. So inside JavaScript, you could actually go and make a remote call. And that was particularly important for some of the things that we were doing. The reason that we added it to start with was that we needed a way to be able to lay out a database. And the JavaScript that we got did quite a decent job of laying out a template database where you had nothing there to start with. You know your realm, you know the admin password. Well, here's everything that Active Directory needs. And so scripting became a really important part of Samba as we started to extend on the complexity of both that and other things. So we used a lot of JavaScript, but this graph's not doing what the other graphs were doing. Something went wrong. You see, the cool kids were using Python. We were really quite ahead of our time for once, so we moved from JavaScript to Python. And
once again.
Yes. It was, and this time, Tridge was subdued, there was some chloroform involved, and some small lies were told about there's a mystical Python debugger that was going to make all of our lives easier, because we were sick of debugging this JavaScript thing that you had to basically jump into GDB and sort of figure out where you were in the JavaScript.
Not to mention the embedded Python.
Oh yes, we promised that we were going to include Python into Samba, so it wasn't a big external dependency that you had to rely on. That if you didn't have it, there'd be Python would be packaged with us. So anyway, we got it in. We were able to make the move, and Tridge has actually become quite a fan of Python. He now programs Python in his spare time when roasting coffee beans and doing other things. And for us, working in Python, having an exception-based language has been so much cleaner in some of the code, business logic code that we've had to do. And our love of Python has continued. We've even gone to a Python-based build system known as WAF. This has completely changed the way Samba's built, and Python has really become our language. So, IDL compiler, like I was mentioning before, IDL generation. So we now have massive swathes of Python that's generated just ready to use. If you're writing a piece of application logic and it needs to access a remote server, well, you just say, I'd like to connect that server and do this remote call. It's all there. So it makes it very easy to walk through new things that have to be done. We've also added handwritten bindings for our key internal elements. LDB, our LDAP-like database, has Python bindings for everything that it does. Our TDB layer also has Python bindings. This is a lower level database layer, and it's important to be able to get to that when we need to. Again, despite being a separate project that had never seen talloc before, we've managed to integrate talloc into Python. And so we import a Samba object and say, this has been allocated with talloc, and we give it to Python, and the right thing mostly happens. I say mostly, there is some really nasty bug that we still haven't fixed. Essentially, all the useful parts of Samba now can be accessed with Python. If they can't, we add it into a glue layer. It's not always the most pretty, but we can get to those functions to get our work done, and then someone hopefully helps us put it in the right place later. And we're moving towards more Python scripts. Things that we were doing in C, we're now doing in Python. For example, we've got a tool, Samba tool, that is our administration binary. It's sort of the one tool that does most things. And it went from being an all C tool to being a Python tool that wraps just C where it has to. And that slow transition has also allowed us to make it much more regular. The Python subclassing and things just brings so much more power than what we were doing in C. And Amate was involved in a lot of that work, and a number of others, trying to get us consistent. And by using a proper object-oriented language has had some great advantages. We've also decided that where there's a small task that needs to be done, and it's best done inside Python, we basically we have Samba fork off, a small Python child that runs a script and does something. A big advantage, you can then just run that script later. As long as you use the same arguments, you can debug it, which has been really quite convenient for some things that are business logic-y stuff that weren't time critical or accessed for the clients, but needed to be done. And so that's part of our use of Python as well. So here you can see the Python use in Samba has skyrocketed over the time that Samba 4 was developed. The first spike's a little bit of an oddity of the way we merged our build systems together.
So that's where we are today, with lots and lots of Python code. And as a newer member of Samba team, that's where I jumped in. So I'm going to take you on a small tour of how Python is actually being used inside Samba through some of the examples. Now the first example which I worked on soon after I joined the team was we had Samba 4 provisioning code which could create a DC, and then you could join Windows to it and so on and so forth. And we had the old Samba 3 file server code which is working fine, and people wanted to now migrate from Samba 3 to Samba 4, or rather NT4 domains to Windows Active Directory domains. Now, so we had a bit of a code which was a bit clunky, which could do some configuration migration, it could migrate some of the old databases, but we didn't have a core which migrated all the users and groups from the old NT4 domain. So, and till now, most of the Python bindings were actually developed for the Active Directory part of the code base. So, rather the source 4, the version 4 part of the code. So we first time actually added Python bindings for Samba 3 code, which is the old NT4 file server code, which allowed us to actually extract all the users and groups very easily from Python. And once that was done, we could actually write an upgrade script from NT4 domain to Active Directory domain in just under 2 weeks. Second example, which Andrew mentioned, that we are now even gone to use Python as a build system. So just to sort of give you a flavor of what build rules look like. So every build rule in WAF is basically a Python function. And so we have actually extended the original WAF to include a sort of a glue layer which provides easy functions. So developers can create libraries or create groupings as subsystems. So one of the more challenging part, or rather more interesting part of using Python in a build system is that it allows you to create all metadata as objects. So now, at one shot, you have access to all the targets, their dependencies, and this allows us to do cool stuff. Things like, for a library, you can actually do compile time ABI check. So let's say a developer modifies some library code and tries to compile it, and then once it's tested and all that. Now, when actually it compiles, it not only builds the shared object, but also builds the ABI at runtime. So it takes the shared object, extracts the symbols, uses GDB to actually create the signature for each ABI, and then it compares it with the stored ones to see whether it has changed. So that alerts the developer if any of the symbol has changed, then it's time to either change the minor version or a major version. Now, if obviously if you have removed a symbol or modified a symbol, then you need to up the major version. Or if you have added a new symbol, maybe you should update the minor version. So the advantage is that now developer doesn't have to worry whether any change he has made to the library code, whether it affects all the other dependencies which depend on it. So things like talc library or TDB library, which is now used in many of the other projects. This is another advantage which we get is similar to ABI check. Now we can do dependency tests. So if you are building a binary and it uses many of the dependencies, it could be a subsystem, it could be a library, or so now you can check whether a particular symbol is coming into that binary from multiple sources. Now this allows you to detect that the same symbol is going to get defined twice, and it can avoid some of the very nasty bugs. Similarly, we can also check whether any of the symbols used in the Samba code actually clash with the system, any particular system library which we link with. Similarly, you can do circular dependency check. Okay. So third example is basically the test framework, which you saw a snapshot in the beginning, which actually created a jumble of whole various shell scripts all together. Now it has become a quite complex architecture to understand and to even debug. You'll see in a minute. Now we do two kinds of tests. One is the standard unit test, where you test each component of the code as a library or a subunit. Those are easy to run. You can easily debug them, no problem. But then we want to also test the behavior of the server. So as a file server or as a domain controller, we want to check whether it behaves correctly. Now, for that, we need to actually set up Samba server. We need to run Samba server and then run tests against it. Now, this requires that you need to set up the environment correctly. Now, as an NT4 domain, you can create a domain, or as an Active Directory, you can create many different types of domain controllers. So we need to create an environment for each of those types and then run tests against them. Now, one of the issues is that we don't want to do this as root. So we want to be able to run tests as a normal user. So which means now we need a way to run multiple servers. So if you run mech test, it actually creates 7 or 8 different.
At least. Yes. It's at least 7 or 8, and it's growing as we need more combinations and more complexity.
Yeah, so it creates those many different environments, and so each environment is set up with a different IP address, different subnet, different port, or whatever, so that we can simultaneously do all this testing one after the other, and rather not have different machines running different types of environments. So to do that, we have socket wrappers, which basically fake the IP addresses and also fake socket connections. So all the socket connections are actually wrapped as Unix domain sockets. So with these kind of intricacies, it becomes difficult to actually run this test manually. So you have to run this in the way the framework is set up, and that makes it also difficult to debug if something goes wrong in a test. So then the question is, how do we do this testing? Okay. And once we have developed this test, 18 months ago or so, these tests were made as part of pre-commit check, pre-merge check, so that every time a commit is made, all these tests are run and ensure that none of the code changes actually breaks any of the regression.
This has been a major change to Samba's development. It's the continuous integration has been a bit of a shock to the team at times, but has been made a massive difference to the way that we develop Samba. And that's a Python script. It's a fairly simple script compared to some of the others. It runs over all of our test suites and then submits the job into the tree.
So this is how the test framework looks like. So we have a bunch of tests which are written in Python. So that's the test.py, which basically is a list of all the tests. So now we have we use test tools Python framework to create those tests, And so then there is a Perl framework which glues everything together, which is the self-test PL. And also it sets up the environments. So the top box shows here different kinds of environments, where it's a source 3 DC, whether it's an NT4 domain, or whether it's a function level 2000 DC, or all different kinds of environments. And then you have a bunch of tests. Now, a particular test either needs an environment, in this case, in which case it will connect to a particular server and then run the test. Or if it's a unit test, then it will just run without any environment. And so all these tests run sequentially, and the output of that is then parsed using the subunit framework. So all the tests actually use extended subunit, and then the output is presented in a nice and neat format. So for either human consumption, or when it runs as a build farm, which Andrew mentioned, it can easily be presented as a nice web page where it shows which tests have failed and which tests have passed. So this is just a summary of what I've mentioned. So we use test tools, subunit, which is a streaming protocol for test results. And as of now, we have about 9,000 individual tests, which are arranged as about 1,300 test suites.
One of the key parts of that makes this test framework really powerful is the use of Python for that first layer. Being able to describe a test in terms of a series of loops, for each of these environments and for each of these sets of flags, run this test, reduces the verbosity, and that means that we can cover a lot more combinations without having to hand bang out all sorts of tests.
So we'll see that example in the next, yeah. So here's an example of how do you write a test. So for multiple environments, you create a test suite, and there are 3 arguments. The first is the name of the test, second is the environment which you need, and third is the actual test. Now, as you can see, the test is basically a command line. So it could be written in Python, Perl, Shell. So we have a lot of tests actually written in Python. There are a few in Shell, and most of them are in C. And so on the left, in the previous figure, if you see, on the left, there were test.py functions which listed all the tests. And if you run them just by themselves, they generate this kind of output. So it basically defines each test independently. So you have a test header, the name of the test, the environment, and the command line to execute that test.
And those command lines then, the self-test.pl substitutes in those dollar things based on the environment that's specified in that second line.
Here is an example of test written in Shell. So again, the first screenshot which you saw, which was the output of PS tree, which showed various processes, was actually the result of this particular shell test, which runs a Samba tool, which is a Python script, through a shell script, and then interacts with a DC local, which is a local domain controller environment. And the contents of this shell script looked like, tested is a small function which basically takes few arguments, but it allows you to easily write tests in whatever is convenient for those particular type of tests. So whether it's a shell, or whether you have a torture test written in C, or it could be just plain Python tests. Okay. So I mentioned that when you have an environment test, you need to set up the environment. And that is a bit tricky to set up because of the socket wrappers and things like that. So we have created ways in which you can set up the environment for debugging purposes. So let's say you run your make test and realize that one of the tests fails and would like to know why it fails. So one is whether the output it generated is sufficient, for you to figure out whether, what was the cause of that test failure. If not, you would like to rerun that test multiple times to see what's happening, maybe even run it through debugger. So for that, we have this test end option to WAF. What it really does, it takes an optional argument of which environment you want to set up, and it sets up the environment, so that means it actually provisions that DC, and then gives you a shell, if you don't specify an X term, which basically has all the environment variables set up correctly so that you can connect to that Samba server. And then you can run a particular test multiple times, and since the Samba server is running, you can even attach a debugger to the Samba server and and debug the server code. So there are just few convenient options, and one of the most convenient options is when you are debugging remotely, is -- screen option, which allows you to create multiple screens for each of the sessions. So it actually creates two screens. In one screen, it runs the server itself, and in another screen, it gives you a shell where you can run the client and run multiple tests against the server. Okay. Now, this is the last example. So we talked about this build farm. So what exactly is the build farm, and how do we actually use it? So when we actually do commits in the Samba code, it runs make test slightly different format, which is actually called auto build. And if it passes, then the code is committed or merged. But now we would like to also test that this code runs across multiple platforms, multiple OSs, so that we can be sure how good the code is tested, how well the code is tested. So for that, we have this build farm, which now these are the machines people have with spare cycles. There are various machines, various architectures, various operating systems, and each of them runs a cron job. Now this cron job basically pulls the build farm scripts, downloads them, and then also downloads various repositories which you want to test. So it could be the bare Samba 3 code or the Samba 4 code with different compiler options. Could be GCC or could be a native compiler. And then it runs those tests, parses them, and then uploads them onto a central site, which is the central site, which is the build.samba.org, where you can see the results of these tests on various machines. So
we're not really a C project after all, but at least we're not C++. So on that note, we wondered if there were any questions. Yeah. Okay, up on the left.
Okay.
Sorry, hard to see people in the light.
So I noticed you set up a number of environments for testing against. Do you reuse those environments, or are they set up freshly for each test?
Now we have to reuse them because they can take a couple of minutes to set up.
Okay.
And so at an hour and a half, our test suite is long enough without resetting them up. This does create some challenges if the tests corrupt each other. But it's the only choice we really have.
Do you have a deterministic test order?
Yes, the test order is deterministic, and we have a way of running a subset of the tests, which sometimes helps when one triggers in another. If you can guess what they are, you can run just the two of them, which is better than waiting an hour and a half for the next failure.
Well, good. Has anyone else got any questions? Absolutely no one? Okay. I think we'll wrap it up now. Okay, now on behalf of the conference team, I would like to thank you two very, very much for your effort and your time.
Thank you.
And thank you.